Hello guys, welcome or welcome back to my YouTube channel. Sorry for that loud clap. Yeah, so we are going to study waves and sound in this chapter, and we are back with a new physics video, not economics. I'll be soon posting economics video. So we are back with physics video. Today's topic is waves and sound, and my name is Dwaj Jain. I'm from India. Like, share, subscribe to my YouTube channel. Comment down good stuff about my video, and don't be selfish. Go forward it to your friends. Like, send the link. Do not download this video. Okay, I'm telling you, do not download. Anyways, let's go forward. So what do we mean by waves? Okay, in a layman's language, like anyone would say, like the waves of the ocean, and the sound would be like I'm speaking. That's a sound. Okay, the sound is coming through the earphones into your ears, so that's also a sound. So, but sound in physics is a wave, and a wave in physics is basically it carries energy from one location to another location in the matter without carrying itself, okay, or without carrying the matter itself, okay. So it's just transfer of energy in the medium or in the matter. So let's go forward and learn about the types of waves. What are waves? We are going to study about sound, and first type of wave that we are going to learn is the transverse wave. So the particle vibrate and the vibrations are um, perpendicular to the progression. Okay, so it's so the energy is moving from like here to here. So it's moving like that, right? Okay, so this is the movement or the progression, and this is how the uh, this is how the energy is moving. Okay, so the up and down motion of the rope is perpendicular to the direction of the wave, basically, if you can see right here. Okay, so you can look at that. So I will just erase this so that it does not look disgusting. Okay, so this motion and the direction of the wave or the direction of the energy transfer, they are perpendicular. Just look at that. Okay, they are perpendicular. Okay, so the particle vibrate and the vibrations are perpendicular to the progression of the wave. Progression of the wave is the direction of the wave. One example is light wave. Light waves actually move in like this. Okay, okay. Next, longitudinal waves. What are longitudinal waves? The particle vibrates and the vibrations are parallel to the progression of the wave, like sound waves. Sound wave is the example. The waves are bunched up sections in coils with stretched out sections in between. These sections are called compressions and refraction. As the name suggests, compression would be the bunched up section, and refraction is the stretched out section. Oh, well, okay, yeah, found it. So this is actually bunched up. This is compression, and look at these are rare fractions. Okay, and when you need to find a wavelength of the wave, you take it from one point and you take the equivalent next point. That would be the wavelength. Over here we have taken a point in between of the compression, right? So we will take a point in the next compression just between that compression, and that distance would be called as wavelength. You can do the same thing with the rare fraction. If I take this, and if let's say 1 2 3 4 5 6 7, okay, 2 3 4 5 6 7, so this would be one wavelength right there. Okay, that would be one wavelength that we need to measure to get the wavelength. Okay, next we have so we have learned about types of waves, but we need to learn about the features and the waves. What do we have in a wave? Like frequency, wavelength, and amplitude. Okay, so frequency is the number of waves passing any point per second. Unit hertz. Okay, so look at, wait, is there a diagram? No. Okay. Okay, so look at this. When we have, let's take a graph kind of thing. Okay, I will just plot it like this. Over here, if you have time 1 and 2, let's say, and if I am drawing a wave, for example, so I know it's not even, but just take it like that. So this, for example, this is one wave. Okay, so this would be 1 hertz frequency. Okay, because in 1 second only one wave is passing completely, so that would be 1 hertz. um, okay, so the unit would be hertz, the spelling and the unit is given. Time for one oscillation is called period. Period is equals to 1 by frequency. So basically, if I need to find the period of this wave, then this would be 1 upon what's the frequency, which is 1. Okay, so the period would be 1. For example, oh sorry, what have I done? That's like the worst mistake in my life. Okay, yeah, so for example, let's just take that the wave has a frequency of 2 hertz. So the period would be, where is the thing? Okay, so the period would be 1 by 2, which is equals to 0.5. Okay, so that's period. Wavelength, this is the distance between any point on a wave and its next equivalent point. So as I have told you over here, I have explained you how can you find wavelength. So you need to take a point and the equivalent point on the next wave, which is the wavelength of a wave. Next we have amplitude, the maximum and minimum displacement. So when we have a wave, let's just take a wave right here. So the amplitude is this distance. Okay, this distance which is marked. Okay, not marked basically, but yeah, let me just use a different color, like the distance which is given in green. Okay, so that's the distance, or that's the maximum minimum displacement, which is known as amplitude. Okay, next we over here we have a very clear image where we can see the amplitude, which is this is the wavelength, this is the, okay, when we have this type of wave, which is a transverse wave, we have, when it, the bump goes up, that's called the crest, and when it goes down, it's called the trough. Okay, so that's just like parts of a wave. Longitudinal waves, okay, longitudinal waves, we need to see, like, in longitudinal waves we have it very differently. So over here the wavelength is given, compression and refraction is given. We need to find out the, okay, okay, so we need to find out the amplitude. So the amplitude is given. If you need to increase the amplitude, then we need to decrease, or we need to compress the compressions, and we need to spread out the rare fractions, so that would increase the amplitude, and that's how we find amplitude. Okay, so when the amplitude is louder in a longitudinal wave, then the rare fractions spread out more and the compressions compress more. Okay, let's go to the wave equation that we are going to learn today. Okay, so the wave equation, speed is equals to, I'm so bad at this. Yeah, so speed is equals to frequency into this thing is lambda, which represents the wavelength. Okay, which represents the wavelength. Lambda is a Greek letter, if you don't know. Okay, it's a Greek, I'm just trying to make it perfect. Okay, yeah, so it's a Greek letter for wavelength. So speed is equals to frequency into uh, wavelength. So if we know that period, okay, period which is equals to time, which is equals to 1 by frequency. Okay, or frequency, then we can write that frequency is equals to 1 by time. Wavelength, on the other hand, is the distance, right? It's a distance. So this will give this, if we rewrite it again, then it would be speed is equals to distance upon time. Okay, over here we have a really easy, uh, we can say a really easy triangle kind of thing that we have seen many times. Okay, so this triangle explains everything. If you need to find the velocity, then velocity in this and speed, if you need to find that, then you need to multiply frequency into wavelength. If you need to find frequency, velocity upon wavelength. If you need to find wavelength, velocity or speed in upon frequency. Why am I explaining this so much? Never mind. Okay, next we have wave effects. Okay, wave. If we know, like light is also a wave, it behaves also like a wave. Uh, let's just forget that it's also a particle. Um, so we know that light reflects, refracts, okay, and diffracts also. So it's a wave effect. So this same happens with the longitudinal waves. Reflection of a wave is the change in the direction of waves upon striking the interface between two material. When a wave strikes any interface between two medium, the bouncing back of wave is termed as reflection of waves. I know this is really simple. It's not ray. First of all, it would be wave. Okay, incident wave. Okay, and the reflected wave. This is the medium that they are get reflected upon, reflected from, upon. Reflection is really easy. I guess you guys understand reflection. So in exams they will give you like a material like this, and they will give you an incoming wave or wave like this. Okay, I will just extend this, and they will draw few of these compression refractions. They will not draw like, they will draw it like this. You need to complete this. For this you need to first reflect this ray, and then on the same, with the same angle, you, with the same distance between two lines, you need to draw it again. Okay, so first step, you need to draw the line, reflected ray. Second, you need to make the line at the same angle. Third step, we need to keep the wavelength the same. Wavelength would be this. Okay, wavelength would be this. We need to keep this same between each and every line. It should be same to this. Okay, this. Next, we have refraction. Okay, refraction of a wave involves a change in direction of the wave as they pass from one medium to another. Refraction or bending of the path of wave is complied by change in speed and wavelength of the wave. Okay, so when there is refraction of a wave, two things change. Okay, wavelength, wavelength and the speed. Okay, wavelength and the speed, these both change. So the wavelength changes, speed changes, frequency remains constant. Okay, it does not change, frequency remains constant. If water waves are passing from deep water to shallow water, they slow down. Okay, so deep to shallow, they slow down. Okay, so deep to shallow, slow, they're moving towards S. So shallow, slow, shallow, slow. Okay, you get it. If the end is shallow, then it would be slow. If the end is deep, then it would be fast, of course. Okay, the waves will get faster. See, I'm trying my best to like make this chapter easy, make your understanding easy. So I have just made this up like S, slow, and all that. If you can remember the paragraph that's written in front of your screen, i I really don't want to even get into that. First of all, I would never get into that. I would just choose a really easy way to learn. Okay, to learn and ace my exams. That's the motive at last. Okay, um so yeah, when the speed changes, the wavelength also changes. So speed is proportional to wavelength. Okay, if speed increases, wavelength increases. If speed decreases, wavelength decreases. Next we have diffraction. So diffraction refers to various phenomena that occurs when a wave encounters an obstacle or opening. It is defined as bending of waves around the corners of an obstacle or through a, I don't know what that word is, aperture into the region of geometrical shadow of obstacle of the obstacle. Okay, that was nothing. Even I did not understand. Okay, so diffraction over here they have shown that the wave is coming in and it's diffracting. Okay, it's diffracting. So they are spreading out. But this, I have enlarged this picture for a reason. Okay, don't study this first of all. We need only these two. Okay, only these two. So the first thing, it shows that wavelength, let's just take a wavelength of, let's say, 1 centimeter. I have 4 waves in incoming wave, and I have a gap. That's a gap. Okay, gap of only 0.5 centimeter. Okay, so when the gap, when the gap is smaller than the wavelength, the waves would diffract in a circular motion. Keep that in mind, it's really, really important. Okay, and when you draw these arcs or the circular, yeah, basically the arcs, you need to keep it in the multiple of the wavelength. In the sense, if this is, this should be 1, this should be 2, this should be 3, this should be 4, the radius I'm talking about. Okay, okay, so when the gap is smaller than the wavelength, there is a circular motion. But when I have the same diagram on screen, okay, when I have the same diagram with a larger gap, okay, with a larger gap, like, look at, wait, no, that's wrong. With a larger gap, you know, the effect would be reversed. This, it would go like this, like a staple pin. That's how I can relate to. Okay, this should be curved. Okay, this part, it should go like a staple pin. Let's, for example, this is 2 centimeter, this gap. So when the wavelength is bigger than the gap, no, wait, I will just, okay, let me just write it for you. I don't need it. Okay, so let's just write it down for you guys. It would be much simpler. Let me just add equation to it. Okay, when the gap is bigger, or let's just say, yeah, when the gap is bigger than the wavelength, let's just take this symbol. Okay, God, we don't have wavelength. Yeah, so we have wavelength over here. When it's bigger than the wavelength, there would be a staple pin kind of diffraction. I know this video is getting long. You can, if you want, you can skip this part if you have understood what I have said. If the gap, or yeah, if the gap is smaller than the wavelength, then it would be a circular diffraction. That there would be a circular diffraction. Okay, yeah, so let's move ahead. Next is sound wave and its nature. So what do we know about sound waves? Okay, so sound are caused by vibrations, longitudinal, they are longitudinal waves. Sound waves need medium to travel through, of course. uh, Sound waves can travel through solid, liquid and gas. Sound waves can be reflected and diffracted. We have seen all of these already. It does this. It is a longitudinal wave. It is caused by vibration. It travels through a medium. It's, as I've told you already, it travels, it transports energy and travels through a matter. Okay, so it travels through a medium, which is a matter, but it cannot travel through vacuum. Okay, it cannot travel through vacuum. If you know, you cannot like hear sound, because the sound vibrations would not be passing because of vibration in space. Let me specify, in space, it, all matters are given over here, or all mediums are given over here: solid, liquid and gas. Okay, so that's the nature of sound. Speed of sound depends on the temperature of the air. If temperature is more, speed of the sound is increased. This is not a, it's a proportionality symbol. So temperature increases, speed of sound increases. If temperature decreases, speed of sound decreases. It does not depend on the pressure of the air. I'm saying area. Why? Does not depend on the pressure of the air. Okay, that's, I guess that's pretty clear. I don't have to explain you. Depends on the type of material. So solids are like the fastest. Solids are the fastest. They travel the fastest, and liquids faster than the gas, and that gas, of course. Next we have echoes. So what is echo? Reflection of sound means you can hear the echo or the sound again when it hits a hard surface. It takes time to hear the echo after the original sound is sent and reflected. Speed of echo, distance into 2. upon echo time. So for example, if the distance over here is say 1 meter, actually at 1 meter the diffraction won't take, let's just take as 20 meters. Okay, then we need to multiply it by 2, because it's, see, over here first is going 20 meter and then coming back 20 meters, so that's the distance, right? And echo time, so is the time taken to hear back the echo, the time taken to hear the echo. Over here the man is like, for 1 second it's going there and coming back at 2 seconds, so 2 second is the echo time. Next we have frequency and amplitude. Frequency and pitch are basically synonyms. Human ears range are 20 hertz to 20,000 hertz. That's the range. Amplitude is like you can increase or decrease. So low amplitude, low, the distance or the maximum minimum displacement is small, and high amplitude, maximum minimum displacement is high. Over here we have the, where is this, okay, yeah, so in 1 second only one wave is crossing by, but in that same thing over here two of them are going. Okay, so the pitch is increased, frequency has increased, so high frequency. Okay, so you guys know one of the specialities that I do in my all videos. I have not specified in my previous video that I take up questions related to this topic. So yeah, let's go forward. Label the letter X. Okay, label with the letter X the marked distance corresponding the amplitude of the wave. Okay, so the amplitude of the wave, you can read the question, pause the video and read the question if you want to. I have read the question, so is nothing. Okay, just read it again. So this is amplitude. Okay, this would be the amplitude, this. Okay, uh, y, the marked distance corresponding the wavelength of the wave. Okay, so the wavelength, one equivalent point to the other. So where is that point? Over here, right? They are at equivalent points, so this would be y. A ship uses pulses of sound to measure the depth of sea beneath the ship. A sound pulse is transmitted into sea, and echo from the seabed is received after 54 milliseconds. The speed of sound in seawater is 1500 meters per second. Okay, first of all, we need to convert milliseconds to seconds. So divided by 1000, if that makes sense. Yeah, so divided by 1000, 54 divided by 1000, that would give us a second. That would give us seconds. And we need to calculate the depth of the sea beneath the ship. So I will just write it like this. It is equals to 2d by time taken, which is 54 by 1000. Echo speed over here is 1500. Okay, my handwriting is disgusting, you know. I'm just writing on the screen using my mouse. So this would be 1500 into 1000 upon 54. So let's just calculate using our calculators, of course. I don't know why am I saying of course so many times. So the distance comes out to be 277 27800 meters, and that's 3 SF. Okay, 3 SF. You need to always round it off to 3 SF. Let's go ahead. We have few of the MCQ questions. So sound wave W has amplitude A and frequency F. X is louder and lower in pitch than the sound wave W. What can be said about the amplitude and the frequency about sound wave X? So it's louder in, so let's just go by the elimination technique. Louder in the sense higher than A. Okay, higher than A. Louder, higher. So it cannot be C or D. Then we have A and B. Now it says lower pitch in the sense lower F. Okay, so it would be lower F. Just synonyms, replace them. So the correct option is B. Next we have a walker can see a cliff face some distance away and wants to estimate how far away it is. He makes a loud noise and times how long it takes the echo to come back. It takes 1.8 seconds. If the speed of sound is 345 meters per second, how far is the cliff? So we just need to rearrange it so that we can find the D. So D is equals to 345 upon, wait, I need to, oh shit, okay, fine, we got it back. So this is not the answer. The answer is 27800 upon 2, which will give you, wait, which will give you 27800 divided by 2. It will give you 13900 meters. Okay, so this is the correct answer. Oh shit, that is the correct answer for this question. I just realized, I'm really sorry. I know that if I'm teaching I'm not supposed to do any mistakes, but then I just forgot about this. Okay, yeah, so let's get ahead, forward, not ahead. Okay, never mind. Okay, then into 1.8 upon 2, so that is the distance from the man or the woman and the cliff. Okay, so 345 into 1.8 upon, okay, so that will give you 310.5 meters. So now we need to round it off, and after rounding off the answer would be D. Next we have which of the frequency ranges below is completely audible by the human who has average hearing. So average human hearing is from 20, okay, 20 to 20, 20,000, right? So 20 to 20,000. We need to check which one of them fall in the range. Does 200 to 200 kilohertz? Look at this. Kilohertz in this means that we need to multiply it by 1000. That is like 200,000 kilohertz. So of course it does not fall in the range. 5 hertz to 50 hertz, no, it's not in the range. 50 hertz to 5 kilohertz, 5 kilohertz means 5000 hertz. Yes, this is the option that can be. 50 kilohertz, wrong. We'll just cancel this. It's like really high. Just like this. So the correct option is C. A high frequency note is played on a violin. The violinist then reduces the frequency of the note. What change is the note in the note do the audience hear? So the pitch, the frequency has reduced, so the pitch has decreased. Volume increases, volume decreases, no, not at all. It is completely related to the amplitude. If they are not talking about the amplitude, then just eliminate those options. We just need to focus on frequency. This is one of the mistakes that most of them might make. Like, okay, one thing I have also made, like few mistakes like these. but then it was really uh, old. um, so yeah, but then after practice I have learned the skill of elimination. I have checked, does it match the condition? No, if it does not, just eliminate it, so that you need to choose between only two or three things, okay, which makes your answer much accurate, much easier to get, okay. Next next this is one of the paper 4 questions that I have added, okay. So approaching the gap, on figure 7.1, draw the pattern of the wave after they have passed the gap, okay. Look at this. This is the gap, this is the wavelength, this is the gap. Now if you can see, the gap is smaller, like, just check, the gap is smaller, so the wave, diffracted wave, would be in a circular motion, okay. And I am keeping track of the wavelength. This is the wavelength of the diffracted wave, okay. That's the number of waves that you draw, that you can see. You need to draw those many, okay. One, I've drawn. Two, three, I need to draw more. Two, like, see, my drawing is not perfect because I'm drawing on screen. I hope you guys can understand. If you are doing this in your book, if you wish, if you are wishing to, you can. Uh, it's a really nice question. You need, the number of waves that you draw carries a mark. Then the arrows, and the third mark would be for the shape of the diffracted one. This correct, this wrong, okay. That's for 3 marks. Like, understand, 3 marks in your hand if you do a really simple diagram. Then there are follow up questions on these, that you need to find the wavelength, or like this. So it's really easy if you do the diagrams correctly. In the whole paper 4, if there are, let's say, few diagrams, there would be like 10 marks only for diagrams in your paper 4. That means uh, you have 10 marks out of 80, which is like 12% of your paper. Like, just imagine, your paper can be so easy, and you can get more. Okay, so yeah, so bye guys. Do check my previous physics video. Do check out my economics playlist that I have made, and yeah, stay tuned on my channel. I know this video is the longest video that I have posted in my on my whole channel. So I'm really sorry to waste so much time, but yeah, I guess it was really fun to learn today, and the mistakes here and there, we improved together, we learned together. So I really hope you guys like this video, subscribe to my channel, share this videos to your friends, don't be selfish. Comment good stuff about my video, like you liked it, it's good, nice efforts, anything like that. I would of course reply to your uh, comment. Do follow me on my Instagram, link in my description down below. And yeah, so I will just say bye to you guys, okay. And do check out this video, okay. These are really good. And okay, fine, I'll go.